Okay, so we've been looking at frequency response for the past few lectures now. And as promised, we're going to start to look at some applications of the frequency response concept. But before we do, we kind of have to take a step back and think about the types of systems that we can describe and analyze using the frequency response concepts. Earlier in the course, we spent a great deal of time modeling mechanical systems and developing differential equations of motion, as well as studying the transfer functions in the S domain. And what we learned is that some basic tools for modeling mechanical systems involve using force analysis or free body diagrams to analyze all the external forces, as well as Newton's law, Newton's second law in particular, which states that the sum of the forces equal the mass times the acceleration. Um, there is no reason we shouldn't expand this discussion to include electrical systems, even though this is a mechanical engineering course. There are several electromechanical systems that mechanical engineers deal with on a day-to-day basis. For instance, the typical DC motor is an electromechanical system in that it has mechanical elements to the motor and the housing, but also it's an electrically driven device with some internal dynamics as well. So I think it's very important for mechanical engineers to be able to analyze electrical systems using things like Kirchhoff's current law, Kirchhoff's voltage law, and Ohm's law, for instance, so that we have a more complete picture. And once we have a more complete set of tools for analyzing mechanical and electrical systems, then we're more capable of doing a full analysis on electromechanical systems like DC motors, for instance. Okay. Um, it also turns out that electrical systems are very um, sort of conducive for studying the effects of the frequency response, and we'll see why in just a little bit. Um, uh, One hint that I can give you so far is that we've already studied the first order low pass filter, um, which is essentially a signal processing type of concept where we build a simple RC electrical system, um, and the inputs and the outputs are both voltages, but we can see that the frequency response concepts apply very well to those types of systems. Okay, so we're going to spend a little bit of time over the next couple of lectures in this sort of domain with the electrical systems, because it's a great way to reinforce some of our frequency response concepts as well as prepare us for dealing with some electromechanical systems later on. Okay, in order to analyze electrical systems, we need to do a very quick review of the most typical components that we see in electrical circuits. Resistors, capacitors, and inductors all have different properties. They all do different things, and it's important to know sort of the laws that govern each of those components, right? So, a resistor is governed by Ohm's law, capacitors governed by the capacitance law, and we have a similar law for inductors. And the idea is that with these components, we can kind of configure them into different structures so that basically we produce circuits with outputs to our liking. Right? So if we need to design a certain type of filter and we understand how um, these components interact, we can more easily design those filters. Okay, so what we'll do now is we'll actually take a look using these components. We'll take a look at a simple example. Um, but before we do that, we'll just briefly touch upon a topic that we mentioned earlier in one of the lectures earlier. And that's the idea of the simple low pass, first order low pass filter. Okay, so if we look at a transfer function of the form a over s plus a, by now we should be pretty comfortable with this idea of the Bode plot for this transfer function. Um, and we should be fairly familiar with what it's supposed to look like. Okay, so we know by this point this is one of those 7 fundamental transfer functions, and the Bode magnitude plot will look something like this. And the Bode phase plot will look something like this. Okay, and the main idea here is that this is a low-pass filter because it will allow, and we verified this for a few frequencies in a previous lecture, it will allow all these low frequency components to pass through with the same magnitude as the input, right? The magnitude for all of these is 1. So the output amplitude of the sine wave will be the same as the input amplitude. Moreover, the phase will be unaffected. So the output essentially equals the input for lower frequencies. The reason it's called a low-pass filter is because this particular Bode magnitude plot indicates that we only allow those lower frequencies to pass through. And if we consider applying an input at a much higher frequency, we can see that the magnitude or the amplitude of the output sine wave is going to be severely attenuated, right? So this is 10 to the 0. This, down here, this may be 10 to the minus 4. So we're still going to get a sinusoidal output as a result of applying a sinusoidal input, but at a much higher frequency, the amplitude may be orders of magnitude smaller, which means that the output has been severely attenuated. So for that reason, we call this a low-pass filter. Effectively, it only allows low-frequency signals to pass through it, which is why it's called a low-pass filter. But that was the one filter that we talked about during that lecture because it happened to be equal to one of those 7 fundamental transfer functions. However, there are uses for filters other than low pass. In other words, you may have an application where you only want to allow high frequencies to pass through. In other words, you may want to sort of attenuate low frequencies and only allow high frequency signals to pass through, right? If we're speaking in terms of, say, an audio system, if you're building a nice fancy audio system, you don't want to send your entire music file or whatever music you're streaming, you don't want to send that entire signal through, say, a tiny tweeter speaker. If you just have a little tiny speaker which is only capable of reproducing really high frequencies, then you don't want to attempt to pass a bunch of low frequency content through because it simply can't produce that range of frequencies. So before your source audio reaches a tiny tweeter speaker, you may want to pass it through a high pass filter so that you're really squashing down all those low frequencies and you're only allowing those high frequencies to pass through. Okay, so that's just one example off the top of my head of when you might want a high pass filter. But the high pass filter Bode plot is not one of the 7 fundamental transfer functions. Okay, so we spent a little bit of time discussing how to combine some of those fundamental transfer functions together to produce different transfer functions, and hence those will have different Bode plots. All we're going to do today is explore how we can create some of those other types of filters using these basic electrical elements that we've outlined here. Okay. So for this first example, let's try to produce a high-pass filter which will only allow high frequencies to pass through. Okay, one of the ways we can do this is the very simple RC high-pass filter. It's a very simple circuit. You could actually build this at home if you have a resistor and a capacitor. And the basic schematic is like this. Okay, so you've got your input voltage, which is the voltage measured across these 2 rails, and you've got your output voltage as measured across these 2 terminals. You have one capacitor and one resistor in this configuration. Now, in this configuration, we're assuming that no current flows this way, and that our measurement is basically exact. We're not allowing any current to flow this way when we take that voltage measurement. So all of the current in this circuit flows through both the capacitor and the resistor. And for that reason, we call this an RC series high-pass filter. Okay, so all of the current basically goes through the capacitor and the resistor as if they were in series. In order to generate the ODE that governs this circuit, it's a different way of thinking than earlier in the course when we wanted to do mechanical systems. So if we had a mechanical system, we would look to do force analysis by drawing a free body diagram, and then we would apply Newton's law to generate the differential equations. For electrical systems, there aren't any physical forces, so to speak. So we have to treat them a little bit differently, and we have a different set of tools that we can use. Some of which come from these governing equations for the electrical components, and some of them come from different tools like Kirchhoff's current and voltage laws, as well as Ohm's law. And we just need to use those tools strategically to generate a differential equation for this. Okay, so one thing we might do is start with the capacitance law that says all the current that passes through the capacitor C is equal to the capacitance C times the time derivative of the voltage drop across it. Okay, so our first equation is going to come from, maybe I is a poor choice of terminology. We'll say our first equation will be I is equal to C dV dt. This is just the fundamental capacitance rule for a capacitor. But our dV dt, remember this specific to our circuit, is the time derivative of the voltage across the capacitor. Okay, so the voltage across the capacitor for this picture is actually the difference between V in and V out. Okay, so we can make the appropriate substitution here and just rewrite dV dt as V in dot minus V out dot. Okay, this is dV dt for our particular setup. For the resistor, we get another equation, and the resistance is governed by Ohm's law. Okay, so basically V, we know that V is equal to IR, but V again represents the voltage drop across that resistor. Now essentially, if we've defined the voltage across the output pins as V out, then these are just two rails in parallel. So remember that voltage drop in parallel are equivalent. So the voltage drop across these two output measurement pins is equal to the voltage drop across the resistor as well. So we would modify this by saying V out is equal to I times R. Okay. Now what we've done here is we've sort of went through the circuit once and exhausted all of our components and extracted as much information as possible. And that's left us with two equations. And what we're trying to do is to develop the relationship between the input voltage and the output voltage. So we're just trying to eliminate this current I as a variable. That's relatively easy to do because we have one equation in terms of I, and we'll just plug this in where we see I in the other equation. And what that gets us is an equation that only contains V in and V out and the corresponding time derivatives. Okay, so if I just make that simple substitution, I end up with a differential equation that looks like this. Right? This becomes our differential equation that governs the input voltage to the output voltage of this particular circuit. Now, if we were to try and develop the transfer function for the relationship between V in and V out, what we're looking for is a relationship of output over input. So we want the Laplace of V out divided by the Laplace of V in. Okay, which means we need to take the Laplace transform of both sides of this equation. For the time derivative, we end up getting S times big V of S. And again, we're neglecting initial conditions right now because we're deriving a transfer function. Plus 1 over RC, V out, which is the symbolic representation of the Laplace transform of little v out of t. All of that equal to S, V in of S. So this should be very much a review from earlier in the course when we studied the Laplace transform in depth. Okay, so the fact that the differential equation now represents an electrical system, whereas before it described mechanical systems, doesn't matter. Mathematically, we take the Laplace transform the same way. Okay, so what this gets us is a transfer function, Vn, the transfer function from Vn to Vout is equal to S over S plus 1 over RC, like so. Okay, so this is the actual transfer function that governs the input-output voltage relationship. Okay. From here, we now have the tools to be able to analyze a frequency response. So what I mean by that is we now know how to sketch the Bode plot for this transfer function here. And even though this is not one of the 7 fundamental transfer functions, as I mentioned before, any transfer function is capable, mathematically speaking, of being factored down into a product of those 7 fundamental transfer functions. Okay, so let's go ahead and do that. Let's name this transfer function P, just to represent the plant dynamics. And then on a line below, we can break this up a little bit. Okay, so P of S is equal to, now what I see is, I see a first order denominator. So I've got S plus 1 over RC in the denominator here. Now if I'm gonna compare this to one of those 7 fundamental transfer functions, this looks very much like P sub 1, A over S plus A, right? So first order denominator. However, what I want is to have the term A as well in the numerator. So I'd like to see a 1 over RC in the numerator, and it's fine to put one there as long as you compensate outside for that. Okay, so you're not changing the system at all. And then the only thing that I have left to consider is the transfer function S. Okay, so this is one of those special transfer functions. It has a Bode plot that looks like this one down here is P sub 6. Okay, so we know what the Bode plot for S by itself looks like. We know what the Bode plot for A over S plus A looks like. And we also know what the Bode plot for a constant valued transfer function looks like, right? It's one of these special transfer functions as well. Okay, so what this means is we ought to be able to sketch the individual transfer functions for each of these. We'll call this P sub A. We'll give these some names here. P sub B, maybe P sub C, okay? So just like in the previous lecture, we can now go ahead and superimpose the Bode magnitude plots and the Bode phase plots just like we did in the examples prior. Okay, so let's see how that works. Okay, so we just need to superimpose all of these Bode plots together, which means we should start by sketching the asymptotic approximation for all of these. For P sub A, remember, RC is just a constant value. So a constant value, the Bode magnitude plot, is a horizontal line at that constant value. So assuming the product of RC is greater than 1, we can just place this value where we think it may be. Obviously, this is symbolic for the time being because we don't know the actual numerical value for RC. But what we do know is that the Bode magnitude plot is horizontal. So this will be the Bode magnitude plot for P sub A. For P sub B, we know that we have a first order transfer function with the first order polynomial in the denominator. So our asymptotic Bode magnitude approximation will start with a horizontal value of 1 for all frequencies, and then at the cutoff frequency of 1 over RC, we will start to attenuate at a slope of negative 1 decade per decade. So that's our P sub B. And then P sub C, which is an interesting one. this is one of those special transfer functions. Okay, so this is going to have a constant slope of positive 1 for all frequencies, and it will pass through a value of a magnitude of 1 at a frequency of 1. Okay, so if we're going to assume the value of RC is greater than 1 as depicted here, then 1 over RC is going to be less than 1, so that would put 1 somewhere to the right of that value. And then we just have the Bode magnitude plot for P sub C, like so. And this kind of goes in both directions, right? So a slope of positive 1 decade per decade, and this is the Bode magnitude plot for P sub C. Okay. What's left to do now is, again, to superimpose all of these asymptotes graphically. And because it's the magnitude plot, and we had to do that special trick where we took the log of the magnitudes in order to make it a summation, we have to remember that we are essentially superimposing according to the slopes. Okay, so this is still a product of values. We're just visualizing it as a sum on the log-log scale. Okay, so what we have is, let's get our total Bode magnitude plot. We've got, we can superimpose. Let's superimpose P sub C and P sub B first. Okay, and then deal with P sub A later. Okay, so if we're just dealing with the green and the magenta line, that means for all frequencies less than 1 over RC, we should be following along directly with the green plot, right? Because again, it's a product of 1 times whatever this value is. So that's just going to ride along this value. The other way to see it is that it's a slope of 0 plus a slope of positive 1. Okay, so as we sketch up here, we reach a frequency of 1 over RC, at which point we see a slope of negative 1 being superimposed with the slope of positive 1, which means those are going to cancel and we're going to level out. So right here we have the asymptotic approximation for the product of PB and PC. Now we just need to superimpose this new plot with the P sub A Bode magnitude. And for this one, you really need to visualize this as a product, right? It's a product of whatever this value is with every point along this plot. So the overall effect is that it increases, or it raises up this entire blue asymptote by this amount, RC. Okay, so ultimately what we're going to get is something to the effect of this. And we may not end up exactly on the RC value because our it depends on where the cutoff frequency actually is. Okay, so keeping it general, I'm not going to align it with RC, but the point is that we basically slid this entire asymptote up by multiplying by this amount across the board. Okay, so this becomes our Bode magnitude asymptote, and then we just need to remember that the overall Bode magnitude plot is not the asymptotic approximation, but rather at the corner frequencies we have this smooth roll-off. Okay, so I'm going to do the overall Bode magnitude plot in red, and it's going to look like this. Which, if we refer back to our picture of what a high-pass filter looks like, it agrees very well. Okay, so you have sort of attenuating frequencies below a certain value, and then above a certain frequency, we allow all those frequencies to pass through. Okay, so this circuit here is effectively a first-order high-pass filter, as depicted by our Bode plot here, which is indicated in red. Okay, so above frequencies denoted by this cutoff frequency of 1 over RC, we should expect to see most of those frequencies pass through. The phase is much easier to consider. The phase for P sub A is simply zero. For constant value transfer functions, there is zero phase contribution. So we really only need to superimpose the phase plot for P sub B and P sub C. Furthermore, the phase plot for P sub C, which is the derivative transfer function, which is just S by itself, has a constant phase of positive 90 degrees. So this phase plot is actually relatively straightforward. From P sub C, we just have a phase that's positive 90. That's the phase of P sub C. And for the phase of PB, this is our first order low pass, actually. And so we have a phase plot that should look like this. Starts at 0, ends at negative 90, passing through minus 45 at the cutoff frequency. Okay, now when we superimpose phase plots again, remember this is just direct graphical superposition. So our total Bode phase plot will just be essentially this magenta plot raised up by 90 degrees. Okay, so that's all we should expect to see, like so. Okay, so this becomes our Bode phase plot for P sub C. This is our Bode magnitude for P. I'm sorry. Yeah, this is the Bode phase plot for the overall transfer function P, and this is the Bode magnitude plot for the overall transfer function P. Okay, so we've now created essentially a first order high pass filter using one capacitor and one resistor in this particular configuration. Okay, it's a very interesting circuit as it pertains to the frequency response. We can do a similar thing for second order systems as well. Okay, so we can take a look at some what are called RLC circuits, which it should be no surprise is going to incorporate a resistor, a capacitor, and an inductor. Okay, so if we look at a series RLC circuit, that looks something like this. We've got a resistor in series with an inductor in series with a capacitor, and our measurement is across the capacitor. Okay, so we have voltage out across these pins, voltage in across these pins, one resistor, one inductor, one capacitor. And because this is a series circuit, all of the current is expected to flow through each one of those components. Okay? The way we're going to handle this circuit is to use Kirchhoff's voltage law, which basically says that the voltage drop across the entire circuit should be equal to the input voltage, right? So the total voltage drop goes to 0, which means that the equation can be set up as V in, which is our initial positive voltage. You're going to lose some voltage through the resistor, you're going to lose some through the inductor, and you're going to lose the rest through the capacitor. Okay, so the governing equation is V in minus VR, which is the voltage across the resistor, minus VL minus VC is all equal to 0. Okay, so that's the governing equation that's stated by Kirchhoff's voltage law. What we need to do now is make some substitutions. Okay, so the voltage in, that is what it is. The voltage across the resistor, that's easy because we can state that using Ohm's law. Okay, so we have V in minus IR, that's the voltage drop across the resistor. The voltage drop across the inductor is given in the equation for the inductor. It's going to be L times di dt. Okay, so L times the current, the time derivative of the current flowing through it. Now the interesting thing is for the capacitor. Well, we've been given the expression in terms of the current for the capacitor. Okay, so for the capacitor, the law is I is equal to C times dV dt. If we wanted to solve using the capacitance law for the voltage, we would have to actually integrate both sides of this to solve for the voltage across a capacitor. Okay, so we can actually do that, and it seems like it may get pretty complicated, but we're just going to apply it and then and then we'll handle it a little bit later. Okay, so dealing with essentially solving for the voltage in that capacitance rule, we get 1 over C times the integral of I dt or d tau. Okay, so this is basically for all time prior. Okay, so this is just, it looks a bit messy right now, but this is a symbolic representation of the voltage across a capacitor. Okay, and this was derived just by taking the integral of both sides of the capacitance law. All of this should equal 0. We'll call this equation A. Now, what happens is, okay, if we want to get rid of this integral, like if we want to not have to deal with this, one thing we can do is take the derivative of this entire equation, right? Because the derivative of the integral will essentially cancel the integral, right? We'll be doing opposite. We'll be doing opposite operations. Okay, so we can actually take the derivative of this equation here, and what we end up with is the following. We'll get Vn dot minus I dot, which is strange to write, but this is just the time derivative of the current, R, minus L I double dot, because we're taking the derivative of di dt, minus 1 over c. Now the derivative of the integral of I of tau just becomes I of t. Okay, so this helps us simplify the equation, right? So this is basically just di dt. I'm sorry, we're just taking the time derivative of this equation in A to get this equation below. There's nothing that's preventing us from doing that. Okay. So if we go ahead and solve, okay, if we solve for, if we put all the stuff with Vn on one side of the equation and the stuff with I on the other side of the equation, we can generate a second order ODE in terms of I and Vn. So we'll write it out this way. I double dot plus R over L I dot plus 1 over LC I is equal to 1 over L Vn dot. This is an ODE. This is a differential equation that expresses the input voltage to the current flowing through that circuit. Okay. From here, if we take the Laplace transform of both sides of the equation, we can see pretty quickly that we get a transfer function that relates Vn to the current. Okay, so we're going to get the transfer function from Vn to I of S, and this should look like S over L times S squared plus RS plus 1 over C. Okay, so this is just going back to taking the Laplace transform of the differential equation to get your transfer function. Okay, however, even though we have a transfer function, this is not the transfer function that we want. We want the transfer function from Vn to Vout, not from Vn to I. Okay, so there's a little bit more work that we have to do here, but it's relatively straightforward, because if we go back to our circuit, we can just analyze this area to develop a relationship between the current and the output voltage. And actually, all we have to do is apply the capacitance law to get that. Okay, we know that I is equal to C dV dt, but the voltage in this case is equal to the output voltage. Right? The voltage across the capacitor in this picture is Vout. Right? It's the same across parallel rails. The voltage is the same. Okay, so Vout is defined as the voltage across these pins. It's the same as the voltage across these pins. Okay, so I is equal to C V out dot. Taking the Laplace transform of this, we get capital I is equal to C S V out of S. Okay, so very straightforward on this one. And from here, we can actually solve for the transfer function from I to V out. and that's going to be equal to 1 over CS. Okay, 1 over CS. The reason we wanted to do this is because ultimately the transfer function from V in to V out can be expressed as the product of the transfer function from V in to I times I to V out. Right? We're allowed to do this as the Laplace operator is a linear operator. Okay, so we just have to multiply this times this, and what we see is that our overall transfer function from V in to V out has the form of 1 over LCS squared plus RCS plus 1. That equals P of S. Okay, and now what we're starting to see is that dynamically speaking, this is the same thing as a second order mass spring damper system, right? Dynamically speaking, it's the same form of the transfer function. So this is equivalent to, say, your traditional mechanical analog, which is like a mass spring damper system, right? Which has the same form of a transfer function. So that's interesting to see. Furthermore, we actually know what type of filter this is, right? We know what the frequency response or the Bode plot looks like for this circuit because we actually can see that the transfer function here has the same form as one of our 7 fundamental transfer functions. And so we can see that essentially we've got a second order low pass filter. Right? So we know that this Bode plot, at least the magnitude, Bode magnitude for this, is going to look like this. It's going to have a sort of a second order attenuation. Now, you would have to pick your components R, L, and C such that you do not introduce a resonant peak, because generally speaking, if you're trying to design a filter that's only intended to squash out higher frequencies, you don't want to have a band or a range of frequencies that you get amplification. That would be a poorly designed filter. So you want to choose your R, L, and C such that you have a scenario where there is no resonant peak. Okay, but that's relatively simple to do because we know the criteria for resonance in our second order systems. Okay, moving right along with some additional examples here. The electronic oscillator. Right? The electronic oscillator is one that's used in many systems. So whether it's wireless communication or signal generators or radio frequency transmitters, you often want to generate a particular frequency of output. And so essentially what's happening is that you can convert a DC or a constant input to an alternating output, right? So you can use basically a constant input to produce a sinusoidal output, right? Now our mechanical analog for the oscillator is like a pure, an undamped pendulum, like so a purely oscillatory system where, say, you have a pendulum or a mass spring damper with no damper, right? You completely unbolt the damper and put it in a vacuum. Now if you apply a constant force, you're going to get pure sinusoidal oscillation in the output. In the electronic realm, well, that's sometimes a very desired trait. Sometimes you want to convert a DC signal into an alternating output or a sinusoidal output. Okay, so if we were to consider this transfer function that we just analyzed, one way to do that would be to eliminate the damping term. And we can eliminate the damping term by setting R approximately equal to 0 or eliminating the resistor entirely. Right? If we eliminate R from this transfer function, we're left with 1 over LCS squared plus 1, which we know has imaginary poles, so we know that we can expect pure oscillation in the output. That is precisely what happens in the so-called LC oscillator. Okay, the LC oscillator is exactly the RLC circuit we just looked at, only we remove the resistor entirely. Okay, so if you put components in this configuration, theoretically, without even doing the full analysis, we should basically have this transfer function without the damping component in there. Okay, and so that's exactly what you get. This circuit here has a transfer function, which we'll call P of S, equal to 1 over LCS squared plus 1. Now this is your second order undamped transfer function. So it's basically a mass spring damper system with no damping, or it's a pendulum with no aerodynamic drag, or in this case it's an electronic circuit that produces harmonic outputs. One thing that's nice is we actually have the tools, and this is the last thing that I'll leave you with. We have the tools to verify if this is indeed an electronic oscillator. Okay, so going way back, we can bring some things from earlier in the course to verify that this is indeed an oscillator. Okay, so if we have a DC or a direct voltage in, so if we just have V in is equal to 1, so we just have a constant voltage, right? We just have a constant voltage going in. What we want to happen for that voltage going in is to produce a sinusoidal voltage in the output. Okay, that's the purpose of an electronic oscillator. Okay, so we can verify that that's the case by actually doing a bit of forced response. Okay, so if the voltage in is a constant value, we know that the Laplace transform of V in is equal to 1 over S, and then we can go ahead and solve for V out in this expression here. So V out should be equal to our transfer function, LCS squared plus 1, times V in, which is 1 over S. Okay, and of course we would need to do a bit of partial fraction expansion to express this as the sum of several simpler terms. For example, A over S plus BS plus C over this quadratic term, LCS squared plus 1. Right, so using our partial fraction expansion from way early on in the course, we can see that we can get the same type of a result here. Okay, so using our methods that we already know, common denominators equate numerator coefficients, we can solve for the coefficients. In this case, we'll do it symbolically. B is equal to minus LC, and C is equal to 0. Okay, so our actual voltage out, big V of S, in the Laplace domain looks like 1 over S minus LCS over LCS squared plus 1. Now what we need to do is write this in a way that looks like it's something on the Laplace table. So we may go ahead and make this substitution. Basically divide both top and bottom by LC. That way it looks more familiar. We get S over S squared plus, now it would be 1 over LC, but we'd prefer to write it as square root of 1 over LC squared. Now this thing here that we've produced is exactly one of the entries on the Laplace table. Okay, so at this point we know the inverse Laplace of this. We know the inverse Laplace of this, so we can go straight to V out of t by taking the inverse Laplace. And of course that gets us a constant voltage, and this is the key here, plus or minus a sinusoidal function. So we actually get a cosine of this particular frequency. Cosine of, this ought to be square root of 1 over LC t. And so we can see that the actual output voltage is going to be sinusoidal. Right, so it'll look something like cosine starts at 1, 1 minus 1, so it'll start at 0, and it'll go like this. So it'll be purely sinusoidal. and we know the frequency, so furthermore, by your choice of L and C, you can specify the actual output frequency of your electronic oscillator. So we've converted this sort of constant DC voltage to an AC or alternating voltage in the output. Okay, so that's an example of applying these electronic systems. We looked at the electronic oscillator as well as how to produce a high pass filter, as well as we looked at the full second order RLC low pass filter as well. Okay, so we are just starting to get into these electronic systems, and I want to stop here before we get too far into it. But in the next lecture, we'll start to analyze more filters, and we're not just going to look at low pass filters and high pass filters. We'll also consider band pass filters and band stop filters, and we may even look at notch filters and peak filters as well, as more practical examples of the frequency response, just to improve your understanding of the subject matter. Okay, so we'll see you in the next one.